Our next speaker is Gian Merlino, is a co-founder of the Imply. Gian evangelized on data and strongly contributes to Apache Druid as a committer and PMC chair. Please welcome Gian.
Hi everybody. Good morning, good afternoon, good evening, whatever time it is where you are. Everything's global now. Everything's global and remote now. So today I'll be talking about hot analytics versus cold analytics, about the temperature spectrum of things, and hopefully it'll be interesting. It's going to be a little bit of a peek into the way that we see the world in the Apache Druid project, and how we see both what's been happening in the past, what's happening in the present, and the future of analytics. So without further ado, first off, who am I? I'm Gian Merlino. I'm the committer and PMC chair at Apache Druid, which is a real-time analytical database. And I'm a co-founder at Imply, which is a company that is built around the Druid project. Today, we'll be talking for about half an hour, and there's 4 things I want to talk about. One is things that you might care about. And the point of this part of the talk is, if I'm talking about things and you actually do care about them, then great, you'll probably be interested in the rest. A stroll down memory lane, so we'll talk about the past and present of analytics. A peek under the hood of Apache Druid, so a little bit about how Apache Druid works, a brief flavor of that, and then can we have it all, a look into the future, potentially, of analytics. So first off, things you care about. So I mentioned the temperature spectrum, and this is actually a pretty core concept in the way that we think about the world. And we think about use cases for analytics on this spectrum. It's less about data sets and more about how you use them. So on the one hand, we have hot use cases, and hot use cases are exemplified by query seconds that need to be sub-seconds, just a few seconds. They generally want to operate on fresh data. A lot of them are going to be streaming. Some may be batch or micro batch, but generally relatively fresh. They are going to be high concurrency. So these are going to be applications that are being used by a lot of users, and they're going to be highly interactive. So we call this online analytical processing. It means that we don't necessarily know ahead of time what all the queries are going to be. We want to provide slice and dice ability to a highly concurrent workload with fast query speeds. On the other side, we have colder use cases. And colder use cases, slow queries are, okay. Speed is always good, of course, but for cold use cases, it might be acceptable for it to be slower. Less fresh data is also acceptable. The concurrency is expected to be lower. So, instead of hundreds of users at a time, we might have just a small handful, maybe even a single user. And these are going to be used more for reporting and planning. On the left here, we have a picture of a cheese warehouse, and these use cases are commonly handled by data warehouses. So I want to talk a bit about what I mean by OLAP and hot use cases. This is on the hot side of things, this is an application that we make an Imply called Pivot. These are some videos of it, and I really like to talk about it in terms of videos because the whole point of Pivot is to be interactive, and the whole point of what we try to do and what we try to power with Apache Druid and with applications like Pivot is interactive analytical experiences where you're not just writing a query and getting an answer, but you're sort of exploring through data, flying through data. And this is why it's so important that the query times be sub-second to just a second or two, because if they're any longer than that, then these experiences become much less interactive and much less valuable. So in terms of use cases for real-time OLAP, there's kind of 2. I really love this image macro format. 2 things coming together. There's really 2 components of that use case: exploration and monitoring. And when I say monitoring, I mean that's operating on very fresh data, almost real-time data. And monitoring is about looking at what's happening currently in a live system, debugging what's going on, troubleshooting, and also just understanding what the state is of a live system. And then exploration is understanding at a more deep level than monitoring. So it's root cause analysis, it's looking at trends, and it's going to be mixing in that historical data. And so exploration is something that may run on both real-time and historical data. Monitoring is mostly real-time, and together these come in for these sorts of analytical applications that we're trying to power. So where is this stuff useful? It's useful in a lot of places. Some really big ones that I just want to pick out here. The second on the top, data-driven applications. That's a really huge one, and that's where I spend most of my time thinking about. The idea here is let's say you want to build an application that is oriented completely around data. Let's say you're trying to build something like Google Analytics, or you're trying to build something that lets a bunch of people log in, see slices of data, explore in different ways. That's where this kind of stuff is the most useful. So the question is a natural question is, why tolerate cold data? If we have systems, I'm telling you that systems like Apache Druid can power these experiences where everything is super fast and fresh and real time and everything is amazing and awesome. Why tolerate cold data? Well, the main reason is cost. So the hot data use cases tend to have very high concurrency. So people using it constantly. These are server systems that are up 24/7. And the cold data use cases, like I mentioned, tend to have very low concurrency. They might just have a single user at a time, or maybe 0 users. And so the cold use cases, because the usage is so low, tend to benefit more from elasticity. And so systems that are optimized for cold data tend to be very elastic, and they tend to sacrifice some performance for that elasticity. So you bring compute to bear when it's necessary. You're going to pay a performance cost for that. But in the long run, the bill will be lower for infrequent access. And then for hot data, access is very frequent. You don't want to pay that performance cost. You want to have it always at your fingertips. And so that is one reason why both of these systems do exist in today's world. Just a little sneak peek at the future, and at the end of this talk, I'll be talking a little bit about how these systems might not be so different after all, even though today that they are. But before we get there, there's some other stuff I want to talk about. I want to stroll down memory lane. I want to talk about the past and disk lane and network lane, of course, because we're not just looking at the past. We're also looking at the evolution of hardware and how the evolution of hardware sort of changes the way that we do analytics. So in the good old days, the very beginning of the analytical world, things are simple. One size fits all. You have a relational database. You put all your data into it. It's probably an old-timey relational database before all the open source ones came about. But you just put everything into it, and you do analytical queries for it. It's your one data store. It's the data store you're using for running the actual business, and it's the data stores you're using for analyzing the business. It doesn't scale very well, but it's very simple. So it's a good place to start. Pretty soon, even before the big data era, people realized that this sort of thing doesn't scale. We're not in the big data era yet, so we're still operating in the realm of relatively classic single server solutions. So what we're going to do is we're going to have one machine that's running our transactional database. We call that OLTP. That's the one that actually runs the business, where we store shopping carts and user profiles and stuff. And then we have a data warehouse. And the data warehouse is going to be a separate machine, and we are going to transfer data periodically from the live database into the warehouse. And the benefit of this is that we separate the live serving stuff from the warehouse, and it means we can build a warehouse that we can do queries on. It's not going to affect our live system, and it doesn't. We're still not in the big data era, so these things are not scaling super well, but it does scale better than trying to run everything on one machine. So it's an improvement. And what happens here is people realize that the data warehouse gets overloaded. Once all the business data is dumped into the data warehouse, people want to do all kinds of crazy stuff with it. It's just one server. It can't really handle that much. And so what people do is they carve out a slice of use cases that we call these OLAP use cases. And this term OLAP is invented around this time, decades ago. And the concept here is we're going to take the data from the warehouse, we're going to put a slice of it in an OLAP database, and then we're going to put applications on that OLAP database, and we're going to store it in a form that's optimized for serving applications. And it's not necessarily going to be able to do as much computation. It might not be as flexible as the warehouse, but it'll be much faster. And so we're sort of seeing people start to make a flexibility to performance trade-off here. Adds another step. So we're going to get data from the transactional store, the live store to the warehouse, and then from the warehouse to the OLAP database. And the OLAP database, this is sort of the world's first invention of a hot analytical system. And it's cool. It still doesn't scale super well. These are still single machine things. But this is what gets us the ability to really push what a single machine can do to the limits. And the limits actually are pretty good. But then the big data era comes and changes everything. And everything becomes parallel. And the big data era, any system that is just a single server is no longer relevant. Everything's got to be multi-server because we're dealing with much bigger data sets. And also people are tired of buying servers with 200 processors in them that cost $50,000. People just want to buy commodity hardware. People want to use virtual machines. So actually servers initially get smaller and we'd have more of them. So the big data era, what happens here is we have a bunch of data sources. Those data sources might still be live databases like they were in the past. They might be streams coming from stuff like Kafka. So we have these data movement systems that are built up to move data around Kafka, Airflow, things like that. We have data lakes, which are pure storage. Which is a pretty cool concept. It's this idea of this, super scale out pure storage system that doesn't do any computation, doesn't understand the data format, just is a place to put it in a scalable way. And then we have query engines that can query data from a data lake. And the very first ones are things like MapReduce and Hive and Spark. And then later on, there's ones like Presto. And I think that even the newer stuff, like the pure cloud-based things that are not things you can install yourself, but you can only get as a SaaS, like BigQuery and Snowflake and things like that, I would say also fit into this model. They also sort of fit into this query engine that operates on remote storage kind of model. So this is the big data era. It's all based around data movers getting things into a giant storage system and then building query engines that query things out of that storage system. It's great. It's super scalable. It has one problem, which is that like the warehouses of yore, the olden days, it's super flexible, but we are not getting the best performance that a machine can offer. The fact that we are transferring this stuff over the network from the data lake to the query engine means that we are having to pay that cost. Networks are getting better, but they are still not as good as local storage, especially when it comes to random access. And so we're not really getting the best that the hardware has to offer. So enter the concept of serving databases. Serving databases store an optimized copy of data and are designed for situations where getting performance is of the essence. We have this is where that trade-off starts to happen that I mentioned earlier, where the query engines are querying data directly out of the lake. And so they're a little bit more elastic, and the serving databases are storing a copy. And so they're a little bit less elastic, but they're faster, get performance more close to the metal. The very first serving databases that people use in the big data era are things like HBase and Cassandra are pretty popular for this kind of thing. Those, at least for analytical stuff, those are still very popular for sort of point queries, for I just want to retrieve keys and values. But for analytical stuff, databases, a next generation database is designed specifically for analytical serving, like Druid, like Apache Druid, are popular in the space now. Druid is, and some of the other things that are in this space, generally support two modes. So not just loading from a data lake and storing a copy of data from a data lake, but also storing a copy of data directly coming from a streaming source like Apache Kafka. So when people are deploying analytical serving databases like Druid and similar systems, sometimes that copy of data is being copied off a lake, and sometimes it's bypassing the lake completely and coming directly from a stream. And so why do people do this? People do it because it's fast. People do it because you take two things that are thought of as query engines, Hive and Presto. Hive is a bit older, of course, and Presto is a bit newer. Presto is the newer one, is faster. But Druid is still 24 to 59 times faster than Presto on the same data set. And so that is why you would want to use a system like this. You're wanting to get performance that's much closer to the metal. And again, what's the point of cold data? And I just want to come back to this concept of we'll come back to it a couple more times, but it is that elasticity, and that is really what's useful there. So the idea is that for a use case, if you think about cost, every let's say you have a data set, let's say you have a use case where data is being queried very frequently. It's being queried, hundreds of times per second, or maybe slightly less than that, but still hundreds of times per minute. And this is happening 24/7. So this is a system that's always going to be online. And you're trying to get a certain level of performance. So what you're going to want is a system that is always online and that gets performance as close to the metal as possible. That might be, a 10 server Druid system. And it's possible that, given these speed advantages, to get the same performance as that 10 server Druid system, you'll need a 100 or 200 server Presto system. And so the Druid system is a clear winner because it's 10 servers instead of 200 servers. And where systems that are more query engine like start to have an advantage is when you're querying them very infrequently. Let's say the system's not online all the time. Let's say it's not always being used. If that is the case, then let's say you're making 10 queries a day, and the system is going to be online for just an hour a day. In that case, you'd be better off spinning up a system or running a system where you can scale it up, do a query, then scale it back down. And that query is going to take longer than it would on a system like Druid, but you don't need the cluster to be running all the time. So that is a kind of going back to this cost and frequency of access concept is why people tend to have why both of these systems still do exist in today's world, and people haven't all gravitated towards one or the other. Okay, so let's see. I want to talk a little bit about Apache Druid, how it works. Let me check time. I think I'm about halfway through, so that's perfect. And I'll talk a little bit about Apache Druid and how it works. So Druid's purpose is to power analytic applications. Like I mentioned earlier, this on the left is implied pivot, and on the right-hand side, we have some other applications that are powered by Druid. So Looker, Metabase, Superset, these are business intelligence applications that have native Druid connectors. And we also support SQL in Druid, so you can write your own applications. And a lot of our users actually are writing their own applications. And I would say it's almost relatively large camps of people doing all three of these options, using Implies app, using a third-party app, or writing their own app. Druid in the wild, it's as a system that is designed for serving large amounts of data at close to metal performance. We are used by a lot of organizations that do have a lot of data and a lot of needs to analyze that data. So here there's nice blogs written by Netflix, Smopub, which is a Twitter subsidiary, and Airbnb talking about how critical Druid is for their workflows. And then some numbers here on the bottom left of just Druid clusters in the wild and what they're capable of. So there's clusters out there that are having 100 billion or more rows loaded per day, trillions of rows retained, spanning hundreds of servers with sub-second to a few seconds of query latency, and doing a mix of streaming and batch ingest. So this is a system that is, it's firmly in the sort of, scalable category of things. I want to do a little flavor of how it works. I'm not going to get into a ton of detail. If you're interested, then you can search around online for some much more detail about how Druid works. But I'm going to talk about a little flavor. So from a high-level perspective, Druid's got a service-oriented architecture. There's a few kinds of services that Druid uses. We sort of group them into servers, because people tend to co-locate related services on the same physical servers or virtual servers. So people tend to have three server types. They tend to have a query server that has a query broker on it, a data server that has what we call historical and index services, and then a master server that has a coordination service. So each cluster is just going to have a small number of master servers just for redundancy purposes. So typically 2 or 3. Most of the servers will be data servers. The data servers are the ones that actually store data, and they're ones that load new data. So they're responsible for pulling new data from streams and files, indexing that data. There's this concept of deep storage on the bottom here. What they do is deep storage is something like S3 or HDFS. We are going to push data to deep storage as a long-term backup and as a way to shuttle data between servers. And then finally, at the top, the query server, the broker, is responsible for actually receiving queries from users, finding the data servers that have data relevant to that query, which might be all of them, or might be a subset, fanning the query out so they each do their part. There will not be a quiz later, but this deep storage concept does prove useful for some musings later on. So keep it in the back of your mind. And then once we get into what's happening at a low level, we have the engine and data format that are tightly integrated. And so this is a graphical depiction of what happens, what's going on inside a Druid table, inside a single shard of a Druid table. This shard has 8 rows in it. You can tell because there's 8 timestamps. There's 8 items in the price counts, artist and city column. This is sort of a data set of ticket sales, various artists in various cities. And when we query this data, one of the things that is particularly cool about how Druid works, and the reason why it can get such close to the metal performance, is because we're very economical with how data is queried. And what I mean by that is, for example, excuse me, you can see that we're actually storing the artist column in 3 different ways. One of them is we're storing a dictionary of all the unique artists we've seen. We've seen 3 artists here. We've given them each a number. We're storing a data section where those numbers that we've assigned them are stored. And then we have an index section that is sort of a reverse lookup into the data section. So if we have an artist and want to know what rows match that artist, we can see that. And storing the data 3 different ways is really useful because it means that when we're scanning a column and doing a group by, we can do a group by with number keys instead of string keys from the data section. We can look up the strings later. And that's really great because grouping on numbers is a lot faster than grouping on strings. Computers like numbers and they don't like strings so much. And when we're doing a filter, we can use the index. So between having an index, the ability to operate on this dictionary coded data, also the fact that all of these parts and all of these columns are individually compressed with a compression mechanism that varies based on their data type, means that the way that we do queries is super efficient. Okay, so finally, I wanted to talk about can we have it all? So I talked a lot about when you would want to think about using a hot analytical system, when you want to think about using a cold one. A lot of it comes down to frequency of access and performance requirements, and which one is going to be the most cost-effective system for your performance requirements will actually vary based on the concurrency and frequency of access and all this stuff. But can we have it all? Can we envision a system that enables sort of fuzzing this line a little bit? So let's think about that. Let's go back to this. Let's go back to this picture. Let's look at what makes Druid different from a query engine like Presto. So these query engines fetch data on demand. And Druid will fetch data ahead of time and then partition it and index it. And so Druid, with these partitions and indexes and local storage, is part of what gives it the performance advantage. Both systems are elastic. The query engines are a bit more elastic. Both are fault tolerant and both are shared nothing. So they both have those properties to them. And I didn't talk much about Druid's elasticity, but you can scale Druid up and down. And what will happen is it will move data around as you scale it up and down. And that data movement process generally takes about an hour or 2. So the scalability, I think of it as like how long does it take to scale? Does it take a minute to scale or does it take an hour to scale? And Druid's the kind of system where it takes about an hour to scale. The system's online during that time, for what it's worth. It's just, you're not gonna, I'm just talking about how long it takes for data to be fully rebalanced once the scaling operation has been initiated. Anyway, so what are the advantages of these things? The advantage of a query engine is spot elasticity. So what I mean by that is in theory, because a query engine doesn't have any data stored locally, you can scale it up and down in the order of seconds or minutes. And the ability to query federated data sources. So data sources that you don't actually store a copy of. And what does a system like Druid give you? It gives you better performance in the same hardware. So from if you're not scaling so much because you have very frequent access, and so you're not scaling down very often, you're going to get better performance on the same hardware, better price performance, better cost, and a lower performance floor. Meaning that Druid queries can get all the way down to tens of milliseconds or hundreds of milliseconds, and you're going to be really hard pressed to see a query get that fast from a system like Presto. So that's what I mean by a performance floor being lower. And coming back to this picture, the final thought that I want to leave with is, remember how the way Druid works is we index data, we load data, we index it, we push it to deep storage. We sort of use deep storage as like a backup and fabric for moving data between servers. We don't query out of it. All the queries happen on a local disk. Is there, what's the difference between a query engine like Presto and a system like Druid that gives you the option to query out of deep storage? I think that it's, once you think about the real differences between these systems, how they actually differ from each other. The big one to me seems to be, are we fetching data ahead of time, or are we pulling on demand? And it's interesting that there's not a lot of systems that are able to operate in both modes. And maybe the world needs one. And that's one of the reasons I like working on Druid so much, because we're building the future. And stay tuned. Anyway, if you're interested in Druid, follow the Druid project on Twitter. It's at Druid.io on Twitter. Join the community. You can go to druid.apache.org, click community, see what's going on. And then we're hiring for Druid and Imply. If you're really interested in the stuff I was talking about and you want to work on it full time, go to imply.io/careers. Thank you. Thank you everybody for coming.